Welcome to the session on exponentials and logarithms, general exponential functions and e to the power x. The objectives for this session are to sketch graphs y equals a to the power of x, y equals e to the power of x, and transformations of these graphs. Recall that exponential functions are functions of the form f of x equals a to the power x, where a is a constant. We're going to sketch various graphs of f of x equals a to the power x for various values of a and their corresponding gradient functions, f dash of x equals k times a to the power x. Here's a table giving some functions of the form f of x equals a to the power x and their corresponding gradient functions. Let's sketch these. Here's y equals 2 to the power x and its corresponding gradient function. Notice that the line for y equals 2 to the power x is above the line for dy dx. Here's the function y equals 3 to the power x and its corresponding gradient function. This time, y is below dy dx. And here we have y equals 4 to the power x. And again, like y equals 3 to the power x, y equals 4 to the power x is also below its corresponding dy dx function. So for f of x equals a to the power x, the differential is f dash of x equals k times a to the power x for a constant k. As a increases, k also increases. Now between a equals 2 and a equals 3, there exists a special value e, such that f of x equals e to the power x equals f dash of x. Note that this e is approximately equal to 2.71828 and so on, and is irrational. So here's the curve for y equals e to the x, and dy dx, notice, is equal to e to the x also. We are going to focus our attention on y equals e to the power x. So here's the graph of f(x) equals e to the power x, and of course, as we mentioned earlier, this has the special property that the derivative is also e to the power x. So for all real values of x, if f of x equals e to the x, then f dash of x equals e to the power x also. And using slightly different notation, if y equals e to the power x, then dy dx equals e to the power x also. And for all real values of x and any constant k, we have that if f of x equals e to the power kx, then f dash of x equals k times e to the power kx. And using the same notation as earlier, we have that if y equals e to the power kx, then dy dx equals k times e to the power kx. Now let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's have a go at example 1a first. We are required to differentiate y equals e to the power 5x with respect to x. Notice that we've highlighted the rule that we're going to apply to our example. So let's apply this. we have y equals e to the power 5x. Therefore, dy dx equals 5e to the power 5x. Here we have k equal to 5. Now let's have a go at example 1b. We are required to differentiate y equals e to the minus x over 10 with respect to x. In this situation, k is equal to minus 1 over 10. So therefore we have that dy dx equals minus 1 over 10 times e to the minus x over 10. Now let's solve example 1c. We are required to differentiate y equals 9e to the power 3x with respect to x. Here we have a constant as well at the front, so we leave 9 as it is. However, k itself is equal to 3. And here's k equals 3. And 9 has been left as it is. And so dy dx equals 27 times e to the power 3x. Now let's have a go at another example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 2a first. We are required to sketch y equals e to the power 3x, giving points where the graph crosses the axes, and state the equations of any asymptotes. Here are our two graphs. We have y equals e to the power x and y equals e to the power 3x on the same graph. As x tends to infinity, e to the power 3x tends to infinity also. The y-axis, or line x equals 0, is an asymptote. And as x tends to minus infinity, e to the 3x tends to 0. And the graph crosses the y-axis at 0, 1. Now let's solve example 2b. We are required to sketch y equals 4e to the minus 7x, giving points where the graph crosses the axes, and state the equations of any asymptotes. So here are two graphs. One is of y equals e to the minus x, and built on that is the graph of y equals 4e to the minus 7x. Notice that as x tends to infinity, 4 times e to the minus 7x tends to 0. We also have that the y-axis, or line x equals 0, is an asymptote. And as x tends to minus infinity, 4 times e to the minus 7x tends to infinity. This time the graph crosses the y-axis at 0, 4. Now let's solve example 2c. We are required to sketch y equals 1 plus 3e to the minus 1 over 4x, giving points where the graph crosses the axes and stating the equations of any asymptotes. Here we've plotted two graphs again. In blue we have y equals e to the minus x, and in red we have y equals 1 plus 3e to the minus 1 over 4x. We've used the simpler graph to help us sketch the more complicated one. So as x tends to infinity, 1 plus 3e to the minus 1 over 4x tends to 1. And that occurs because, of course, 3 times e to the minus 1 over 4x is tending to 0. The line x equals 1 is an asymptote, and of course the asymptote has shifted up by 1. Also, as x tends to minus infinity, 1 plus 3e to the minus 1 over 4x also tends to infinity. And this time the graph cuts the axis at 0, 4. Notice that the graph of y equals e to the minus 1 over 4x has been stretched parallel to the y-axis with a scale factor 3 and then translated by 0, 1. This brings us to the end of this session. If you have understood its contents, you should be able to sketch the graphs of y equals a to the power x, y equals e to the power x, and transformations of these graphs. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.